today I'm going to talk about some deformation theory on certain orbifolds called the Coxeter 3-orbifolds. So basically, a Coxeter group is a certain finitely generated group with having certain group presentations, and it has a natural action on some nice spaces as the spheres or the Euclidean space or the hyperbolic space and so on. So the Coxeter orbifolds are basically some orbifolds arising from that action. And then like other manifolds or orbifolds, we can think of some additional geometric structures on that orbifolds and consider the deformation spaces and so on. So I'll explain those things in detail later. Okay, so let me start from the first slide. So I'd like to explain about the convex real projective orbifolds, which is basically the category where our main object belongs to. So in general, so suppose that we are given a Lie group which acts transitively on topological space X. So basically, each element of G is a homeomorphism of X to itself. So in this setting, when we have another orbifold M, by a GX structure on that orbifold, I mean a smooth atlas of charts, which are basically the collection of homeomorphisms of the open subset of M into the open subset of X, such that each transition map extends to elements of G. So there are many examples of GX structures. For example, we have classical hyperbolic structures on manifolds or orbifolds. Or also we have Euclidean structures and affine structures and so on. So in today's talk, I'm going to mainly focus on the real projective structures, where our Lie groups now is a PGL and our X is the real projective space. Or alternatively, we can also think of this setting. So our G is the group of matrices having determinant ±1, and X is the projective sphere. So yeah, by projective sphere, I mean the space of all the half lines starting from the origin inside the Rn+1. So that space becomes a double cover of this real projective space. Okay, so those two real projective geometries are almost the same, but for the sake of convenience in our discussion, by a real projective structure, I mean this the latter setting, the projective sphere together with the SL plus minus. So furthermore, let's say this omega is a convex open domain inside this projective sphere. So by convex, I mean whenever we have 2 points inside it, we can always join them by a projective line segment, which also lie inside this omega. And also suppose that we have a discrete subgroup gamma of this Lie group G, which preserves the omega. So every element of this gamma leaves this omega invariant. So then we obtain an action of this group gamma on this convex domain omega, and that since this gamma is discrete, you can see that this action is always a proper discontinuous. So whenever we are in that setting, that quotient becomes an orbifold. And then that orbifold has a natural real projective structure, which is induced from the real projective structure on this omega. So that orbifold now becomes an orbifold together with a convex real projective structure. So the classical example of this convex real projective structure or convex projective orbifold is a hyperbolic structure. So in that case, this omega is a round disk inside this real projective space. And then whenever we have a convex object, we can think of the Hilbert metric on that omega. And then this round disk together with this Hilbert metric is exactly the same as the hyperbolic space in the Beltrami-Klein model. So this omega is now a hyperbolic space. And also this group gamma turns out to preserve the Hilbert metric or the Beltrami-Klein metric on this omega. So this quotient is not only the real projective orbifold, but also it is hyperbolic orbifold. So my point is that to generate some real projective manifolds or orbifolds, we have to find some convex open domain inside Sn, and also some discrete subgroups of this SL plus minus preserving that domain. So actually, there is a very nice way to construct such examples developed by Binberg in 1970s. So let me introduce those examples, which are called the linear reflection groups. So here, my setting is that we have a convex polytope inside this Sn. So that is basically subset of Sn, which is defined by a finite number of linear inequalities. So alpha 1 to alpha f are the dual elements of this Rn plus 1. So the kernel of each dual elements now becomes a hyperplane inside this sphere. So the convex polytope is the subset which is cut out by those hyperplanes. So here I have drawn one example here. So these three lines are hyperplanes, and then they cut out the convex polytope. And then each codimension-one face is of course supported by the kernels. And then for each facet, I mean the codimension-one face, I choose one vector, another vector inside Rn plus 1 satisfying this relation. And then whenever we have this, we can think of certain linear endomorphism of this Rn plus 1 defined in this way. So this is called the linear reflection. So the role of this endomorphism is that it fixes each element of this kernel pointwise, and also it sends vi to minus vi. So this endomorphism has an eigenvector vi with eigenvalue -1, and then it fixes the hyperplane pointwise. So we think of such linear reflections and consider the subgroup gamma generated by those reflections and call it gamma. And as in this picture, the best case scenario is that whenever we have this gamma and whenever we consider the images of this polytope under the action of this gamma, those images may or may not overlap with each other. So in this picture, they do not overlap with each other, but in general, that kind of thing may not happen. Okay. So whenever when that images does not overlap with each other, we say that this group gamma generated by those reflections is a linear reflection group. So actually, Binberg proved that this, whenever we have a linear reflection group, then that group becomes discrete subgroup of this SL plus -1. And also the gamma orbits, it's drawn in here, tessellates properly convex domain inside this Sn, as I draw with this boundary. So as I explained before, whenever we have such action, then the quotient becomes an orbifold together with the real projective structures. So here in the third picture, that is the resulting orbifold, whose underlying space is exactly the same as the polytope we began with, but it now has a orbifold structure. For example, on each point on the codimension-one face, the local stabilizer group is the Z mod 2Z, and then for the codimension-2 face, that corner is homeomorphic to this R2 divided by the action of the dihedral group of certain order. So actually, for the Coxeter orbifold setting, those integers defining the dihedral group is essentially gives us the whole information on the orbifold. So I briefly I record that data in this way by writing the integer in here. So polytope together with the integers on the codimension-2 faces are Coxeter orbifold. And that Coxeter orbifold now has a convex real projective structure, which comes from this the convex real projective structure on this omega. So in general, for general manifolds or orbifolds, and also for the choice of the geometric structures, we can think of the deformation space of GX structures on the orbifold M. Okay. So basically, the deformation space means the space of all the possible GX structures on M, and modulo the reasonable relations called the isotopy. And then those quotient space is called the deformation space. So one classical example is that when we have this hyperbolic geometry on the surface, then the deformation space is nothing but the tight Müller space. And also in particular, when this surface is closed surface of genus greater than equal to 2, then this deformation space or the tight Müller space is known to be homeomorphic to certain Euclidean space. So I would like to extend this result to the higher dimensional objects, especially on the Coxeter orbifolds. So first of all, to extend this theory to higher dimensional object, we must give up the hyperbolic geometry, because for dimension greater than equal to 3, the manifolds or orbifolds admit at most one hyperbolic structure on it. I mean, more precisely, the complete hyperbolic structures on it. So that is called the Mostos rigidity theorem. So so another geometry we can think of is the real projective geometry, because it naturally extends the hyperbolic geometry. As I explained before, the hyperbolic structure is a specific example of the real projective structure. So that real projective geometry is a natural choice to extend the hyperbolic geometry. And furthermore, our orbifold is a Coxeter orbifold. In some examples, we can compute the whole entire deformation space of this real projective structures. So for this reason, I'm interested in this Coxeter orbifolds. So on another context that of thinking of this Coxeter orbifold is that we can build we can start from the hyperbolic Coxeter orbifold and deform it into the real projective orbifold, and then to generate another non-trivial example of Coxeter orbifold. So actually, a hyperbolic Coxeter orbifold is basically hyperbolic convex polyhedron lying inside this hyperbolic space, and then Andre van Rieven, I'm so sorry. So Coxeter orbifold is basically a convex polytope having some prescribed dihedral angles on that edges, and then the Andre van Rieven found the necessary and sufficient condition where that orbifold can admit a hyperbolic structure or not. So basically, using that theorem, we have a full list of hyperbolic Coxeter orbifolds. So we start with a hyperbolic Coxeter orbifold, and then consider the deformation space of it in the real projective geometry. So that hyperbolic structures on that orbifold corresponds to a point inside the deformation space of real projective structures. And then suppose that we know the deformation space around that point, so that suppose that we have a path passing through the hyperbolic structure, so that along that path, we are basically deforming that hyperbolic structure into the real projective structure, which is no longer hyperbolic. And then we obtain a new real projective structure on the same orbifold. And then since that has each face has a reflection, and then the eigenvector corresponding to eigenvalue -1 lies outside this real hyperbolic space. And then we consider the span of such vectors, and then becomes a codimension-one hyperplane, and then we cut this polytope by that plane to obtain this thing. So we can construct many such pieces, and then we can glue them together to generate another real projective orbifold, which no longer comes from the deformation of these hyperbolic structures. So my point is that by doing such operations, we can generate many discrete groups dividing some certain convex open domain, which is that essentially the hyperbolic ones. So those were the context of thinking the deformations of Coxeter orbifolds. So here are some past results on computation of Coxeter orbifolds done by other people. So if our Coxeter orbifold is two-dimensional, so the polytope is now basically n gone. I mean n the polygon with n edges. In that setting, the deformation space of real projective structures are fully computed by Goldman. So the deformation space of real projective structure is proved to be homeomorphic to Euclidean space, as we've seen in the Teichmüller case. And then also for higher dimensional Coxeter orbifolds, there are some partial results on the computation on the deformation spaces. So for example, Marquis consider certain Coxeter polytopes called the truncation polytopes, which is obtained from starting from the tetrahedron and by truncating some vertices. And in that setting, Marquis computed the whole global deformation spaces. So the deformation spaces turns out to be the disjoint union of certain Euclidean spaces. And also for other Coxeter orbifolds, some partial results such as the local structures around the hyperbolic structure is also known, which is developed by Choi and Lee. All right, so from now on, I would like to explain a way to compute the deformation space using the notion called the realization spaces. So to do that, I have to recall the result of Binberg, which characterizes the real projective structures on Coxeter orbifolds. So so let P be a convex polytope as before, and we have a choice of the linear reflections as before, and we have these eigenvectors corresponding to eigenvalue -1. And then for those things, the group generated by the reflections becomes a linear reflection group if and only if the linear functionals and the eigenvectors satisfy the following relations. So those are basically the linear equalities and inequalities and some quadratic inequalities or equalities. So each configuration of this alpha1 to alpha n and b1 to bf gives us a real projective structure on the orbifold P. And then, yeah, so to compute the deformation space, we need to actually find all the alpha1 to alpha f and b1 to bf, the configuration of those, satisfying these relations. So that's a way to compute the deformation space. So it's written in here. Okay, so in that way, this deformation space can be identified with this the configuration spaces of these functionals and the eigenvectors. So so my strategy to compute this deformation space is to divide this space into partition this space into equivalence classes. So each equivalence class share the same fundamental domain of holonomic representation, so to speak. So more precisely, if we bring an element of this deformation space and forget the last eigenvectors, we obtain the data of linear functionals, which defines a convex polytope inside Sn. Okay, and that convex polytope is a convex polytope which is combinatorially equivalent to the underlying polytope of this Coxeter polytope P. So by that motivation, I have to think about another space consisting of the convex polytopes, and that space is called a realization space of a given polytope. So a realization space of P, or convex polytope P, is the space of all the another convex polytopes inside this Sn, which are combinatorially equivalent to P. So for example, if P is a triangle inside S2, then this space is basically the space of all the triangles lying inside S2. And among them, some of them are projectively equivalent to each other. I mean, the equivalent via the action of this SL, and some of them are not equivalent in that sense. So we think we collect all the convex polytopes inside Sn, combinatorially equivalent to P, and mod it out by the action of this SL plus minus. And that resulting space is called the realization space. So my strategy is to consider the map, which comes from the deformation space into the realization space, given by forgetting the reflection data here in the last part. So the reason that I'm thinking this realization space is that there are some partial results on these realization spaces. I mean, the topological structures on the spaces. So that I can use that result to compute the deformation space in the reverse order. So, for example, if our polytope is two-dimensional, the realization space is actually homeomorphic to 2n minus 8. Here, n is the number of edges. So one heuristical way to see this is that so whenever we are given an n-gon, so to build an n-gon, we have to find these n edges. So each edge, locally at least, has a 2-dimension of freedoms to move. And then if I perturb each edge, that still give us some n-gon here. So we have a 2-dimensional degree of freedom for each edge. So that gives us a 2n. And also we have an action of this SL3R acting on the space. And then SL3R has dimension 8. So I have to take minus 8 over here. So that's our way to see the realization space of 2-dimensional polygons. And for higher dimensional, there are some results as well. So for example, if our polytope is 3-dimensional, we have this following result proved by Steinitz and Filter-Molina. So if our polytope is 3-dimensional, then the realization space can be proved to be a smooth manifold of dimension e minus 9, where this e is the number of edges of this polytope P. So we have a smooth structures on this target space realization space of P. And then to study the deformation space, using that information, we have to consider the fibers of this map. So, right. So each fiber of this map is called restricted deformation spaces. So those are, each fiber is precisely the space of real projective structures sharing a common fundamental domain, so to speak. So in our terminologies, I mean, in our description of this deformation space as a space of configurations of alphas and b's, so each fiber is the space of all the configurations of eigenvectors with a fixed convex polytope here. So so for a given so for a fixed convex polytope, you have to find V1 to Vf. I mean all the V1 to Vf. So one natural and practical way to find such a V1 to Vf is that to find this V1 and to V2 and Vf successfully. So if I recall the relation given by Binberg, we have to find V such that this relation holds. So first, for example, to find this V1, this V1 must satisfy these relations. And then after I find this V1, we find V2 by solving some linear equalities and inequalities and so on. So there is a combinatorial condition called the orderability, which guarantees us that the solution of such linear equations always exist. So under that orderability condition, Choi actually proved in 2006 that each restricted deformation space is also a smooth manifold. So we have a smoothness for both the realization space and also the smoothness of the fibers. So using that result, I was able to construct the smooth structures on the whole global deformation space. So in that setting, that deformation space of the global deformation space is a smooth manifold of certain dimension. So initially, I thought that I conjectured that this natural map from the deformation space into the realization space is a fiber bundle, but there are some examples which disproves that that map is a fiber bundle. So the smoothness is the best thing that we can obtain in this setting, I guess. So still, there is a unsolved question regarding this setting. So we still have to find under which condition on this Coxeter orbifold giving us the non-empty deformation space. So we still do not have a full description of orbifolds which admit the real projective structure here. So okay, that's pretty much what I have prepared for today. So thank you for the attention.
Thank you very much. Let's thank the speaker. Are there any questions for Seungyeol?
Oh, I've just got one question. So, like, the conditions with the vectors v1 through vn looked a lot like the defining conditions for a root system. Is that what's going on under the hood? Yeah, like,
This
here.
condition, yeah.
Yeah. Is it related to root systems in any nice way, or is there a connection there?
Yeah, it looks like some conditions describing the root system, because the root system is also comes from the I mean, there's some sort of reflections, right?
So yeah, it's just like
yeah.
we're taking the faces and then taking something, orthogonal.
Yeah, but actually, I'm not that clear on that connection between those two settings, but this relation comes from the computing the. So if we have two reflections, let's say Ri and Rj, and then if we take the composition, then if we take the trace, then we obtain this relation. I think same thing goes on the setting in the root space, I guess, but I can't. I'm not clear on that connection so far. Sorry.
No, that's okay. That sounds good. Thanks.
Okay. Are there any other questions for Seungyeol? No? If not, let's thank him again.